Have you ever looked really closely at, say, a complex engine part, or maybe a circuit board, with those tiny perfect components, and just wondered how? How do they make this stuff? Well, chances are, behind that incredible precision, there's this kind of silent workhorse. It's the press feed. People don't talk about it much, but it's absolutely vital for the stamping systems that make, well, everything from tiny electronics to huge car parts. So today, we're doing a deep dive into this surprisingly complex world. Our mission, basically, to pull out the most important bits from the sources you've shared, give you a shortcut to really understanding what makes precision stamping work.
You really nailed it there. I mean, the whole manufacturing flow from the raw material coming into the finished part going out, it often just hinges on that perfectly choreographed, almost dance-like movement of material through the press. We're talking about motion time down to fractions of a second, degrees of crankshaft rotation even. And understanding these variables, it isn't just theory. It directly impacts your product quality, your productivity, your bottom line.
Okay, let's unpack this a bit then. What exactly is a press feed? What's its core job in a stamping system?
Think of it as the super meticulous material handler for the die. Its basic task: deliver the exact right length of strip material through that die.
Good on time.
Perfectly timed with the press cycle, yeah. And crucially, without damaging the material.
And the goal is fast, accurate setups too, right?
Absolutely. Least amount of time possible for setup. Now, how it does this, well, there's a whole range. You've got simple hand placement of blanks. You've got automated pick and place.
Right.
The sort of continuous strip feed through what's called a progressive die, and even transferring separated parts between different stations.
That progressive die method sounds key.
Oh, it really is. It's fascinating. It really shows why you need that extreme precision. It's like a sequence of operations happening one after another. First, it punches these tiny guide holes, pilot holes, in the strip.
Okay.
Then, as the strip moves forward, step by step, pilot pins engage those holes. And each station in the die does something different, bends it, cuts it, forms it.
Until a finished part comes out at the end.
Exactly. Which leads to a really important question. What are the absolute must-haves, the critical factors for feeding that precisely? The sources boil it down to 4 main pillars: speed, timing, alignment, and slack.
Speed, timing, alignment, slack. Got it.
And when you dig into speed, it's not just the top speed, it's really about acceleration and deceleration. How quickly can it start and stop? You want to maximize the part of the press stroke where the feed is actually moving the material.
Makes sense.
And, maybe surprisingly, how well you time the roll release for those pilot punches. That can often be the hidden bottleneck limiting your whole operation speed.
Okay, that's where it gets really interesting for me. If these seeds are so precise, why is this pilot release thing such a big deal? What does that even mean? Release for pilots?
Well, you could call it the other half of the feed cycle. It's critical. It's not enough to just push the strip forward accurately. You have to momentarily let it go, just release it. So those pilot pins can engage properly and position the strip perfectly. So it's not just forward and back, but side to side too.
Precisely.
Yeah.
And it also deals with subtle things in the material itself, like camber.
Kimber.
Yeah, that slight natural curve you sometimes get in a coil of material. Releasing lets it relax so it doesn't bind up in the die. And it also compensates if the material stretches a bit during stamping, elongation. The feed can still make accurate moves afterwards.
Wow. Okay, so the timing has to be spot on.
Oh, absolutely razor sharp. Think about trying to thread a needle while someone's still pulling the thread.
Right. Impossible.
If you open the feed rolls too soon, before the pilot pin is fully engaged, the strip might actually pull back towards the coil.
Okay, bad.
Very bad. But open them too late. You could damage the pilot holes, or the pins just won't be able to nudge the strip into that perfect final position.
And here's something that sounds like a real aha moment from the sources. Stripper pressure.
Yes, this is huge.
So the stripper plate holds the material down while the punch works, right?
Exactly. But if you don't have enough pressure holding it down,
The punch, as it withdraws, can actually pull the material backwards through the feed rolls, even if they're closed.
no way. So you end up feeding extra material on the next stroke.
Precisely. It throws your feed length completely off. Total chaos for precision.
So for setting up air pilots, this is vital.
Absolutely. You need really clean air first off. A surge tank helps maintain consistent pressure. And keep your hoses short, no sharp elbows. You need that air to move fast.
Okay.
And here's a key technical point. For high speed, you must use 24-volt DC solenoids with the right valve.
Why DC?
It's down to electrical principles. Older 120 volt AC systems just cycle too slowly. The power wave itself limits the reaction time.
Wow. So your solenoid voltage could literally be the speed limit for your whole line.
It absolutely could be. Those valves need to be fast, consistent, provide enough air volume, and critically, their speed can't change if the air pressure fluctuates a bit. It's all about that rapid, repeatable response.
Okay, so we get why pilot release is so important, but how do you actually fine-tune it, optimize it, especially when you're running really fast?
Right, this is where technology comes in. The sources mention that systems built after January 2014 often have pilot cylinders with sensors built right in.
Sensor, so you can see the timing.
Exactly. You can literally view the pilot timing on a scope, often built into the control.
That's cool.
And for really critical jobs, you can even wire that signal straight into the main press control system.
What if you have older gear without those magnetic pistons?
No problem. You can usually add a proximity switch, just mount it correctly.
Okay.
Make sure you get the right type, PNP for 24 volt systems, NPN for a 12 volt typically.
Gotcha.
Now, what's really key here for nailing the timing at high speed, say over 400 strokes a minute, you really need three things. A reference cam signal from the press, that cylinder sensor signal, and a pilot release output signal that has auto advance.
Auto advance.
Yeah, it basically tells the release to happen slightly earlier as the press speed increases to compensate for the fixed time it takes the air system to react. Rule of thumb is often around 7 to 9 degrees of advance per 100 strokes per minute increase.
Okay, that makes sense.
But here's the bottom line. You really cannot set up an air-operated pilot release properly, especially for high speed, without using an oscilloscope.
Oscilloscope. That sounds intimidating.
It used to be, but honestly, today's digital scopes are much easier. They often have setup files, you can save configurations. All it really does is draw a picture of an electrical signal over time, voltage versus time.
Like an ECG for the machine.
Exactly like that. It shows you the electrical heartbeat, lets you see precisely when things happen. Setting it up just means picking a signal to watch that's your trigger, and the scope starts recording when that signal hits a certain level.
Okay, so let's look at what the scope actually shows you. What are some real examples?
This is where it gets really insightful. If you run the feed with no material in it,
Right.
the scope trace looks clean, you see the feed move, then stop. The motor current, usually shown as a red line, goes back to 0 during the stop time. No drama.
Okay, nice and smooth.
Now, contrast that with a trace where you have binding or the pilot release isn't timed right. You'll see that motor currents stay high even after the feed is supposed to have stopped.
It's still fighting something.
Exactly. And you'll often see this big disturbance like a shock wave ripple through the feed rolls right when the punch hits the material.
A shockwave, like a physical jolt.
Yeah, it's force being transmitted back from the die through the strip into the rolls, and that jolt, that's what causes the material to slip.
Ah, and there goes your accuracy.
Gone. You lose your strip position.
So what's the fix? What does the scope show when it's working right?
The solution is actually quite elegant, and you see it clearly on the scope trace. You open the rolls during the punch.
Let the material move freely.
Let it move backwards just slightly if it needs to, guided only by the pilots. This completely eliminates that feed length variation. It's especially important when the strip naturally gets a tiny bit longer as it goes through multiple stations.
Makes sense. Does the scope show other problems too?
Oh yeah. Sometimes you can see the die itself pushing the material around unintentionally, which highlights a good practice. Always try to clamp the material down securely when you're cutting it to stop any pushback.
Okay, good tip. So connecting this back to overall precision, how do we actually measure feed accuracy? And what can the data tell us?
Well, generally speaking, smaller feeders tend to be a bit more accurate, and smooth rolls often outperform plated ones, less surface variation.
Okay.
But the really interesting thing is that roll feed errors are usually cyclical. They repeat. And analyzing that data, breaking it down into frequencies and amplitudes, can tell you a lot about what's going wrong inside the machine.
Like diagnosing component issues.
Exactly. Say you have a 20-tooth gear driving something. You might see an air spike repeating 20 times per revolution on your analysis. Tells you where to look. Or maybe a resolver that's a feedback device has a speed error. It might show up as, say, 4 cycles of error per revolution instead of 1. Big clue. I remember showing scope traces to a plant manager once, revealing his binding issue. He just stared and said, "It's like looking inside the machine's brain."
That's a great way to put it.
And it is. We actually had a case where the data pointed to a faulty resolver, swapped it out, and boom, machine was back within tolerance. Perfect fix.
Wow. that's powerful stuff. So for someone listening, how can they check feed accuracy in their own plant? Is there a practical way?
Yeah, there's a pretty simple and effective method, the scribe line test.
Scribe line.
Yep, you just need a strip of metal, a good straight edge, and a sharp scribe tool. You set a feed length, maybe 0.250 inches for a typical LC feed, or 0.100 for an LD feed with smaller rolls. Then you scribe a perfectly straight line across the material, index a feed manually, scribe another line. The key is keeping the scribe at the exact same angle to the straight edge every single time. Otherwise, you introduce measurement errors.
Got it. Consistent angle.
Then you measure the distance between the leading edge of each line. You can use an optical comparator or send samples back to the factory for analysis. Perfect data would show, say, exactly 0.250 between each line. Real world, you'll see slight variations.
Right.
Doing it on 3 separate strips helps build confidence. You can average out any tiny inconsistencies from your manual scribing.
Okay, that sounds doable.
Yeah.
So we've gone deep into the why and how of precision. But what about the actual machines? How have feed systems evolved to meet these crazy demands?
That's a great question. There's definitely been an evolution.
Let's start maybe with a quick compare and contrast to the main types we see out there.
Sure. You've got your basic die-mounted air feeds. They're usually the cheapest up front, but they cost a lot to run. Air isn't free. They need regular maintenance, setup takes longer, and they're generally slower, maybe 400 inches a minute tops.
Okay, what else?
Then there were rack and pinion feeds, press-driven, so no utility cost, which was good, but accuracy could be inconsistent, setup was slow. They're mostly being replaced now.
By what?
Well, you have cam feeds at the high end. Super fast, we're talking over 3,600 inches per minute.
Whoa.
Yeah, the cam controls the acceleration and deceleration very precisely. Very low maintenance, too. The downsides. The feed timing, the feed arc, is fixed by the cam. Less flexible, and they're pricey.
Okay, but the real elephant in the room, the big disruptor driving all this precision we're talking about, that's the servo drive, right?
Oh, absolutely. The servo feed is the one that really brings that scoop-enabled precision into practical reality for many applications.
So what makes servo systems so special?
It's that integrated control loop. You've got the servo motor, the drive that powers it, the controller, the brains, and a feedback device. Usually a high-res encoder.
High resolution is key.
Critical. The controller tells the motor exactly what to do via the drive. The encoder constantly tells the controller exactly where the rolls actually are. If there's any tiny error, the controller sees it instantly and corrects it. It's a closed loop.
And the advantages?
Huge. Best accuracy, hands down. Like plus or minus 0.5 of an inch, up to maybe 0.005.
That's tiny.
It is. High speeds too. Standard speeds around 2,400 per minute, maybe 1,000 strokes per minute. You can program the acceleration profile, which is great for delicate, thin materials, protects them.
And setups?
Quick, consistent, because everything length, speed, pilot release timing, even roll pressure is programmed and saved. Features like remote inching, jog to length, they just make setup so much easier. Plus you get programmable patterns, GAG outputs, we'll get to those registration capabilities. And a really important detail, they often use what's called a modified sine motion profile.
Meaning?
It smooths out the start and stop, eliminates jerky movements. Jerking is a prime cause of material slippage.
Right, kills accuracy.
Exactly. Now the initial cost is higher than, say, an air feed, no doubt.
But the payoff is in precision and productivity.
Over the long term, absolutely.
So we've talked feed types, but what about the drivetrain? The stuff between the motor and the rolls? Gears, belts, does that matter much?
Oh, it matters a lot. You're asking how that power actually gets transmitted efficiently and accurately.
Right. How do gearboxes stack up against belts or even direct drive?
Okay, gearboxes. They inherently have some backlash. That little bit of play between the gear teeth, and the shafts can twist slightly under load torsional windup. These things add up. You lose efficiency, maybe 7-10%, even in good designs. And that backlash and windup can actually make the servo motor unstable sometimes. You might hear it buzzing or humming. It affects positioning.
Okay, so gearboxes have issues. What about belts?
Belts are actually very efficient, like 98% usually. Much better. But they can stretch slightly over time. You can get a bit of backlash between the belt teeth and the pulley, and the teeth can deflect a tiny bit under load. You minimize these by using heavy-duty, oversized belts and keeping them properly tensioned, but loose belts can also cause servo instability.
So if gears have backlash and belts can stretch, what's the ultimate precision solution?
That would be the direct drive. It's the newest design.
No gears, no belts.
Exactly. The motor connects directly or almost directly to the rolls. This gives you high torque with zero backlash. High compliance too, meaning it handles tiny misalignments smoothly, no shaft windup,
And efficiency.
pretty much 100%. Better acceleration, lower power use, and the highest precision because nothing wears in the drivetrain to change its characteristics over time.
Sounds almost perfect. Any catch? Maybe cost.
Yeah, the initial cost for direct drive is usually the highest.
Makes sense.
But for applications demanding the absolute top level of precision and long-term consistency, the benefits in performance, reduced maintenance, and energy savings often make it worthwhile. It's about matching the tech to the need.
Okay. What about the rolls themselves? We mentioned smooth versus plated, but there's more to it, right? Are they just solid chunks of metal?
Not always. And no, there's definitely more to it. Take low inertia rolls.
Low inertia. Lighter.
Exactly. Instead of solid steel, they might have a thinner wall or be made of lighter material. This makes a big difference. Lighter rolls can open and close faster for pilot release. They accelerate and decelerate faster.
So potentially higher speeds.
Directly translates to higher speeds, yeah. And they use less power. The sources mentioned small, 2-inch low inertia rolls can save over 11% energy compared to solid ones doing the same job.
Wow.
Plus, matching the roll inertia better to the motor's inertia helps the whole system respond quicker and more precisely.
Interesting. Are there other special roll types?
Sure, you see ring rolls sometimes. They're not solid across, they have gaps. Useful if you need to span over an area of the strip that's already been formed, or maybe avoid running over punch burrs that could mark up a solid roll.
Clever. And roll finishes. You listed a bunch earlier.
Yeah, it's a whole menu depending on the application. Mirror finish, satin. Matte chrome for grip. Carbonite for extreme grip. Teflon for slippery surfaces on delicate materials. Diamond-like carbon, DLC, or titanium nitride for incredible hardness and low friction. Hard chrome plating is common, very hard, like 6670 Rockwell C, can make the roll last 2 to 10 times longer than the base material.
So the finish really matters for wear and grip.
Absolutely. Each one is chosen for a specific reason: material type, grip needed, wear resistance, non-stick properties.
Okay, this is fascinating. We've talked progressive dies, but what about other, maybe more specialized feeding systems? What else is out there?
Oh, there's some really ingenious solutions for specific challenges. Transfer dies are a big one.
Transfer guides. The parts are separated from the strip.
Right. Instead of feeding a continuous strip, the system transfers individual parts between die stations. Usually with complex mechanical arms driven by cams or servos, they can manipulate the part in 2 or even 3 axes for really complex forming.
Okay. What else?
Zigzag feeds. These are brilliant for saving material.
How do they work?
They move the feed mechanism side to side as well as forward, allowing you to nest parts like round blanks much closer together on the strip, like fitting puzzle pieces.
Reducing scraps.
Significantly, sometimes 15% material savings or more. Plus, you can often make whole families of related parts with minimal changeover just by selecting a different program.
Yeah.
Huge efficiency boost.
That sounds incredibly useful. You also mentioned gag dies earlier. What's the story there?
Gag dies are really cool. Think of a single complex die, but actuators controlled by the feed system can selectively engage or disengage different sections of that die on different press strokes.
So you can make different parts from the same die.
Exactly. One source mentioned a customer replacing 50 separate dies with one gag die to make different hole saw blades. Cut their production from 2 shifts to 1.
50 dies into one. That's amazing.
Yeah, or making different lengths of electrical bus bars, all from one tool. It's about massive flexibility and tooling consolidation.
Incredible. What about tricky materials?
Yeah.
Like flimsy stuff.
That's where push-pull systems come in. If you have a really thin, flimsy scrap web, or maybe a very elastic material like rubber or even paper, trying to just push it can cause it to buckle or stretch.
Right.
So a push-pull system has driven rolls on both sides of the die, one pushing in, one pulling out. They work together to keep the material perfectly flat and under control. No buckling, no stretching.
Very clever. Any other quick examples? You mentioned space savers.
Yeah, space saver lines try to eliminate that big loop of material you usually see between the uncoiler and the press. Saves floor space.
Downside.
Often a bit less accurate than a system with a proper slack loop, but sometimes the space saving is worth it. Then you've got things like 4-roll feeds for extra grip, specialized wire feeds with V-grooves for round material, even nail feeds, believe it or not, mounted upside down to handle headed nails.
Wow, nail feeds. The variety is amazing. Okay, so bringing this all together, optimizing your setup isn't just about the feed unit itself. What accessories really make a difference?
That's a great point. A lot of accessories are really about making setup easier and maintaining that crucial strip control during the run.
What are some must-haves?
Electronic cam switches, definitely. Also called PLS programmable limit switches. They're essential for servo feeds. They provide those precise timing signals, when to start the feed, when to release the rolls for pilots.
Okay.
Modern press controls often have PLS built in, along with other useful stuff like tonnage monitoring, dive protection, reporting. It's all integrated.
What about things like anti-back rolls?
Anti-back rolls can be useful. They prevent the strip from being accidentally pulled backwards, maybe by the pilots or if the loop droops too much, but they add cost, complexity, and can sometimes limit your top speed a bit.
Material support, like those Cascade
It's
rollers.
absolutely vital, especially at high speeds. They support the material properly as it comes out of the uncoiler or straightener, give it the right radius, stop it from whipping around.
And guides.
Stock guides are non-negotiable. Simple cam rollers or more specialized strap guides or squaring guides, you need something to keep the material aligned going into the feed.
Okay. What about those length checkers you mentioned? Do you really need one if the feed is accurate?
Good question. A really well-built, well-maintained servo feed shouldn't really need a length checker. It should just be accurate. But they exist. They measure the length after each feed and can make tiny corrections, mostly useful for very long feed lengths where tiny errors could accumulate. If you do use one, it needs to be very high resolution, like a 22-bit encoder, to be more accurate than the feed itself. They can provide useful reports on actual achieved accuracy, though.
Got it. In registration, you called it electronic piloting.
Right. This is huge for pre-printed or pre-stamped material. A sensor looks for a specific mark or feature on the strip. When it sees it, it tells the feed to stop and make a final, tiny adjustment to position that feature perfectly.
For lining up graphics or previous operations?
Exactly. And for high speed, the system has to react incredibly fast. Lock the position within maybe 10 microseconds of seeing the mark.
10 microseconds. Wow. Okay, let's step back for the big picture. It really sounds like the feed line isn't just separate machines bolted down. It's a single system.
That's absolutely the way to think about it, a complete stamping system. And the question becomes, how does all this modern feed technology contribute to a truly well-configured feed line? It's all about how the press, the controls, the feeder, the straightener, the uncoiler, how they all complement each other
Working together.
seamlessly to achieve the big goals: quick die change, guaranteed quality assurance, and maximum productivity. It's that synergy that unlocks the real potential.
And thinking even bigger picture, looking ahead, how does all this connect to broader trends like Industry 4.0?
Well, network connectivity is the first big step, and it's happening now.
Connecting machines to the network.
Yep, that immediately enables things like effortless remote support. We use tools like the E1 Cozy VPN gateway, for instance. It means a maintenance engineer can securely log into a machine remotely, diagnose problems, maybe even adjust parameters without needing a costly site visit. Huge savings in time and money.
I can see that.
It also allows for real-time production line monitoring. Management can see exactly what's running, how efficiently, from anywhere. And even better, it opens the door to predictive maintenance.
Calling for help before it breaks.
Exactly. By monitoring drive status, looking for signs of overloading or unusual behavior remotely, the system can flag potential issues before they cause downtime, moving from being reactive to proactive.
That seems like a massive shift.
It really is.
Wow. We have covered a lot of ground today. We've really taken that deep dive into the surprisingly complex and totally critical world of press feeding. From those tiny, precise movements of pilot pins to the sheer power and smarts of servo drives, and seeing what an oscilloscope can reveal, it's just crystal clear that precision is everything.
Yeah, and we've seen how understanding these sometimes subtle variables like timing or roll finishes, or even just the type of drivetrain, geared versus belt versus direct.
Yeah.
How much that can impact your actual efficiency and your final part quality. It really underscores that even in processes that seem straightforward, maybe just mechanical, there's always this deep layer of sophisticated engineering to explore, always pushing the limits.
So what's the takeaway for you listening? And maybe it's just a reminder that sometimes the smallest, most foundational parts of any system, they often hold the biggest secrets to unlocking better performance, finding those efficiencies. It's about looking for those hidden aha moments, isn't it? And maybe here's a final thought for you to chew on. Think about this relentless drive for speed and accuracy in press feeding, how it's pushed by innovations like servos and digital diagnostics. Doesn't that mirror what's happening across all of manufacturing? constantly pushing the boundaries, figuring out how to do things faster, better, more precisely, one perfectly fed strip at a time. So the question is, what other seemingly simple processes in your world might be hiding similar layers of complexity and opportunity, just waiting for their own deep dive?